So Google Classroom. The way that I will be using Google Classroom, because I know some teachers here in the high school, middle school use Google Classroom a lot. All your assignments are in there. You post your assignments. Everything's done through there. For me, I use Google Classroom more as just a bulletin board kind of thing. Each of the days will have new weeks that are going to post here. And each of those is just going to say, well, here we go. Pretty much this here. So Wednesday, we're covered chapter 5.42. If you missed class today or you missed the lesson, you will need to watch the corresponding lesson video and then complete the homework assignment on this page. And that is, yeah, this is mostly what I'm going to use Google Classroom for. This is a way to update you so that you see, you know that that's there. One of the other things that we do have, I will post kind of if we're having the test or say it's a review day, I will have the review sheet posted there, so if you need a copy of it or lost it, there is a copy of it there, so that you can reference back to it. I will post up that when the chapter test is, when we do have makeup days. This is old, so where is it? Makeup day. I do post a Word doc for the makeup days in there. We'll see if it actually gives us a preview. Section assignment, page number, problem number. So that way, if you are missing an assignment, have something at the end of the chapter, I post that up there. Easy to see, easy to reference. We kind of get how Google Classroom is going to work in here. So there's not a whole lot that I do in it. One of the bigger things is up at the top, the syllabus, the book. Because if you notice, I kept putting page numbers on the homework, on all those there, but you don't have a book. I don't hand out books, mainly because none of y'all in here, I don't think, but every now and then y'all do know students transfer in, transfer out. And most of the time when they transfer out, they take the book. I don't know why you need an Algebra 2 book or would want to take an Algebra 2 book, but they do, and we never see it again. So instead of doing that and making y'all keep up with books, I have the whole book here. So if you lose the homework sheet, you can pull the book up. It does have the corresponding page numbers on it. So like this here is the page 7 is the homework for section 1.1. The note sheet that y'all do have, if you flip to the back page of it, is you see that you do indeed have that exact same page. Because I found it easier to just add the homework pages to the back of your note sheets or to your note sheets than to have you get a full-blown book, because for all intents and purposes it is the same thing, except that is way lighter and not as bulky as a full-on book. Y'all kind of agree with that? Okay. Now, the last time y'all used Big Ideas, they did have the online version of it. Since we adopted the new books and did not continue to use Big Ideas said, cool, you're locked out. You don't have access to that anymore because you have not paid to use that anymore. So we're using the PDF book of this here. The syllabus is here, so if you want to reference back to that. I do have the YouTube channel on y'all's page, so if you click that link, it will take you right to it. I have not added this other piece yet. I will be adding it. Plan book is the new thing that we're using. We started using it. Some of us started using it last year. Some have been using it longer. This is kind of just lesson guide of the week. I will put the link up there so it will show you kind of the week's lessons of what's going to be happening as I put it in. So it kind of gives you an idea of what's going on or if you missed something. It will also give you previous lessons. So this here is for last year, so it shows, okay, for May 5th, and going on, this is what's going on. May not use it, may not reference it at all, that's fine. And luckily, we don't have AMI days, but if we do have snow and they decide to do that, we'll contact that when we get there. Because these are the main things we have right here. Syllabus, the PDF of the book, and the YouTube channel link for class here. We good with all that there? Did I talk about the bonus points yesterday? So bonus points. There are bonus points. I do give out bonus points each week. And you get them by answering the math trivia question of the week. It is on the back wall on the chalkboard. I will create the little sheets of paper. I haven't done them yet, but they will. All you got to do is put your name and the answer on a little sheet of paper. I would show it to me. Just kind of say, hey, Mr. Clinton, did I get it right? Either say yes, you did, or no, and give you some hints on trying to do it again. It's not a one and done kind of thing. It's very much you can answer it as many times as you want until you get it right. Each one of those is worth 2 points. That's it. Just put your name and the answer and turn it in. I would not put it on my desk. The reason I say I wouldn't want you putting it on my desk is because if the answer is not right, I will try to get it back to you. But a lot of the times that's happened, I forget about it between when I see it and the next time I see y'all. And normally you guys don't get the extra credit because you don't realize you didn't get it right. So if you show it to me, I'll say, yes, you got it right, and I'll take it. And I'll put the bonus points in at the end of the week. Or try to remember to anyways. Does that make sense with the bonus? New one each week, and especially on Monday. If by this time, if there's not a new one posted or a new one I wrote up there, let me know. I will put one up there. Because there's a few that aren't math related. But most of the ones that are, all the ones that are going to be straight from the ACT. I take ACT questions and put those up as the trivia question for the week. All right? Questions on this so far? Now, the first chapter we're looking at is chapter 1, 1.1 specifically. Chapter 1's a little bit of everything. It's a little bit all over the map. We are going to talk about intervals and set notation, writing stuff in sets. We're going to talk about systems of equations, matrices, quadratics, family of functions, and it's going to bounce around. But the first thing we're talking about is intervals and set notation. Well, if we're going to be talking about that, it's going to be good to know what a set is. Now, a set is a collection of objects. That is the purest, basic definition of what a set is. It's just a collection of objects. Normally for mathematics, we talk about it in sets of numbers. We can also talk about it in sets of shapes or different things. It's just a collection of objects. And we normally use braces, and braces are used to list a set's members. So we put braces around it to list the set. So if we were talking about a set of numbers, 1, 2, 3, we would normally write it as brace 1, comma 2, comma 3. So we list each element. Each element is each of the members in the set. And we put commas between them just to signify we have 1, 2, 3. And we kind of have to put commas, otherwise if we just write 1, 2, 3, it doesn't look like the numbers 1, 2, 3, it looks like the number 123. Because they would go right together. The other example that we have here is positive even numbers. And our first positive even number would be 0. Then we would have 2, 4, 6, 8, 10, dot, 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 dot. Because with any of these sets, when we write it out as this here, we start with whichever one the first number in the set is. So we start with 0. Then the next one would be 2, 4, 6, 8, 10. Once we've done enough of them, at least 4, to set a pattern, we can do the dot, dot, dot. All the dot, dot, dot says is that this pattern that we've established is going to continue on indefinitely. Because as much as we try, or as hard as we try, there's no way for us to list every possible positive even number. There's just way too many of them. There's an infinite number of positive even numbers. Questions on this so far? All right. Now, to really talk about this here, we need to actually specify the types of numbers, because using the types of numbers will help us be able to identify groups a lot easier. Because there are ways, especially for the set of positive even numbers, to write it simply, write it more condensed. Because in math, mathematicians, for the most part, are lazy. There's no other better way to say it. Because if we can write something simpler, if we can write something easier, we're going to do it that way. Okay? And that's across the board. With even proofs, we're trying to prove that a theorem or something is true. If part of my theorem or what I'm needing has already been proven, all they say is reference his work. I'm not kidding. I'm trying to prove that this is true. Well, he proved part of it first, so see his work if you want that part. And then I'm going to keep proving what I'm proving. The funniest thing is they actually had a mathematician wrote a 400-page proof. Top to bottom said this is pretty much got all the way through. Put it in for peer review, which means colleagues of the same level of degree reviewed it, cut out over 200 pages. Because they're like, yeah, all the stuff that you proved here, cool. It's already been proven. All you had to do was say, see their work, see their work, see their work. Cut it all out. Like I said, mathematicians are normally lazy. Not a bad thing, but they find easier ways to write it, simpler ways to write it. Best case in point is we're going to start with natural numbers. Natural numbers are naturally the numbers you count on your hands and your feet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And we have a short way to write natural numbers. It is an n with 2 lines. So in your first box there, in the dead center, yep. So we're going to write natural numbers. And the shorthand for it is an n with 2 lines. So especially in proofs, or we're proving things and working through stuff, or writing in set builder notation, we'll use this. We won't write out natural numbers. We'll write an n with 2 lines. It's understood to be the natural numbers, or referencing, or we're talking about the natural numbers. You don't have to draw the number line. I'm drawing a number line on both boards, because this here is just a visual to see what we're doing. We're building the number set. Because our natural numbers are our counting numbers, 1 and greater. So on a number line, all we've added are these kind of numbers here going out to the right. Well, you've had Algebra 1, you've had geometry. There's more numbers than just those there, yes? And that takes us to our next type of numbers, which are whole numbers. Can y'all tell what the difference between natural and whole numbers is? There's only one main thing. 0. Whole numbers just add 0. Natural numbers was our n. Anybody have a guess at what the whole number symbol is? There isn't one. But we can use W. Because the only thing that whole numbers added was exactly 0. So whole numbers add 0. So natural numbers are our counting numbers with 1 and going up. Whole numbers added 0. So for the most part, if we're talking about numbers in set builder notation, we don't normally say, if we want 0, we don't talk about the whole numbers. We actually refer to the next group, which is our integers. Integers adds our positive and negative values. So now we're adding -1, -2, -3, -4, -5. And our symbols, natural number was an N. We can say whole numbers is a W, which makes the integer be a, obviously, yes, it's a Z. It's not that obvious. And there's a reason for it, because another number system that we had, we didn't get the integers first, because natural numbers are the ones that came first, so they got the N with 2 lines. Whole numbers, we didn't talk too much about whole numbers. Integers is going to actually come up after the next one. And it's going to be there's going to be a few down, we'll get to it, but our irrational numbers, we actually had irrational numbers before we had integers, just historically. But are we following along so far? With all these, each one of these number sets is building on top of each other. Now, so far we do have integers, but all natural numbers are whole numbers. All whole numbers are integers. That means if a number is a integer, -2, it's not a whole number or a natural number. But the natural number 3 is also a whole number, and it's also an integer. It is all 3 of those. So you see kind of how those flow between each other, because we can have a number be a whole number and an integer, but there is one whole number that's not a natural number. 0. Well, the next thing we're kind of missing are some of the numbers between our integers. So between 0 and 1, or 0 and -1, and those are our rational numbers. Those are our fractional numbers. Anything that can be represented as a fraction, 1/4, 1 2/3, any of these here that can be represented as a fraction are our rational numbers. And just like with all these here, we do have a symbol for it, and it is a Q with a line. R was already taken. We can't use the R with a line for rational numbers. Integers was our Z. We can call whole numbers a W. And natural numbers is our N. Questions on this so far? Now, fractions, we feel like for the most part should cover out most of the numbers between 0 and 1. Yes? Because we can write pretty much every single number between 0 and 1 as a fraction. And unfortunately, we can't really do that. Even between 1 and 2, there are numbers that exist between 1 and 2, 2 and 3, 3 and 4, that cannot be represented as a fraction. One that does come up in geometry a good bit. I don't know if I needed the second. Wow. Is this hiding? I need it. Pi. Circles. We deal with pi with circles, yes? Pi, we normally say is what? 3.14. But it's 3.1415926. It keeps going on indefinitely forever. Can we write that as a fraction? No. We can approximate it, but we cannot write it as a fraction, which means, wrong slides, pi is not rational. And if it's not rational, we call it irrational. There's our I with 2 lines. Does anybody think it's funny that irrational numbers, we had the concept of it before we had the concept of 0? I think that's interesting. Historically, we can say that the Romans did not have a concept of 0. That's why the Roman numerals are so, not complicated, but we have so many of them, and we have having to make, or they kept having to make more new ones for bigger and bigger numbers. They had no concept of 0 or a base number system, because our base number system revolves around 0. But the concept of pi and phi in E, because phi is our golden ratio, they did have the concept of these numbers, these irrational numbers. Those made sense to them. They could figure those out. 0, on the other hand, was a completely foreign concept. The Mesopotamians did have the concept of a 0. They had it, were I think one of the first civilizations we know that had a concept of that. But up to that point, there wasn't a whole lot of reason for that, or integers or negative numbers, because especially in an agrarian, kind of like we're talking about goods and buying stuff, if you had 0 sheep or 0 cattle or 0 of this, why put it down? I just don't have it. So there was no reason or a necessity to define what 0 is. You have 0 of something, giving a symbol for nothing, because that's really what 0 is. It is a symbol to represent nothing. Yes. So phi is the golden ratio. It's the proportion of certain things, and you'll see it in Greek architecture. Just it is a ratio, a circling out. We won't talk about it really. This is the last time you'll see it in this class. E is used for logarithmic functions. It is a very nice version for that, but we won't touch logs until spring. So most of these you won't see. I'm just listing out different types of irrational numbers. There are others we'll look at and see, because another type of irrational number is square root of 2. Square roots are number times themselves. There is not a nice number when multiplied by itself that gives us 2. It's irrational. And so now we've started filling in all the different types of numbers that are between those 0 and 1, are natural numbers, are integers that are not fractions. All right? Questions on this so far? Now, if you notice, all of those are in one big box, yes? Because all of this is contained within the, what we call the real number system. And the real number system does have a symbol. It is an R with 2 lines. That's why rational did not get the R with 2 lines. The real numbers had it first. Now that begs the question, if we have something such as the real number system, that means there also must be what? Hey. And those numbers are off to the side. We call them the complex number system. Complex number system. You don't have to put that down. We'll talk about it later, especially when we get into quadratics and quadratic equations. That is a C with a line, and they come in the form of A plus BI. There are imaginary numbers. There are things such as non-real numbers. Which, as crazy as that sounds, that is something we will actually talk about. You will solve and find solutions that are non-real answers. But questions on our number systems? I think we've covered them before. Y'all talked about them before. It's been a minute. But a lot of the times that what we use this for is to define sets or define groups of numbers, or specify, especially in proof, what number systems we're talking about. What numbers can be filled in for the given variables. Integers also have, rational. Rational. It also is all real. Okay. Let's look at this here. The set of whole numbers less than 10. What is the smallest whole number we can have? 0, yes? So 0. What would be the next whole number less than 10? 1. Then 3, 4, 5, 6, 7, 8, 9, and that'd be it. Because less than 10, so we want all the numbers less than 10. 0 to 9. That's not too bad. We can list those out. So we put braces, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We got them all. All right, the set of odd whole numbers less than 24. So what would be our first odd number? Or listed, yeah, so 1. Then 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23. Listing those out is not bad. It's not hard. We just start with the first odd number and then work our way to the other end. And for this here, all the whole numbers less than 24. Nice and easy to write all those out, yes? So questions on these here. So a lot of times we can use this here and it's very easy to write. There are some, and we'll see some later on in the note sheets where they're not as easy to list out. And some of those we're going to have to actually start using set builder notation to be able to write them all out. So we'll talk about set builder notation before we hit those there. Okay. Nope. All right. Okay. There we go. It decided to erase all that for whatever reason. So a subset is a set that is part of a larger set, is when all of the set members of a set are also a part of the other set. Is when all the members of set A are a part of set B. So we can say A is a subset of B because all of the members of A, all the elements, all the things contained in set A are also contained in set B. It is a subset. It is a smaller group of the larger whole. An example of this that we could say is that Mr. McClendon's classroom is a subset of the high school because everything in my classroom is also contained in the high school, so it is a subset. Okay? We kind of get that there, yes? Can we say that the high school is a subset of my classroom? No, because there are parts of this high school that are not contained in this room. So we cannot say that the high school is a subset of this classroom. Okay? We kind of get that, wrap our head around that. But we can say that this high school is a subset of Concord, Oklahoma. Because everything in the high school, the building itself, is contained within Concord, Oklahoma. Concord, Oklahoma is a subset of Oklahoma. Concord is a subset of the U.S. It can break out bigger and bigger, yes? And if we look at this here in the general sense that we have, set A contains the elements 1, 3, 15, 27, 20. Yes? Subset B, 1, 2, 3, 20, 11, 15, 27, 100. Everything in A is contained, everything in B is contained in A. Yes? All of the elements of A are in B. Now, the way that we write it is we could say set A is a subset of set B. Write the whole thing out. But again, I said mathematicians are lazy, yes? A is a subset of B. That is, yep. It's a little just C, a very small C, kind of, yep. But can we say that B is a subset of A? No, there's numbers, like the number 2 is contained in B but not contained in A. So we cannot say that. We'd say B is not a subset of A, yes? So we need to fix that second statement. You ready for this? Put a line through it. Just like how we said is not equal, we had an equal sign with a line through it. Same thing for this here. B is not a subset of A. Because there's elements in B, in set B, that are not in set A. Okay? We feel comfortable with this so far. All right, here's another question for you. Is set A a subset of set A? Yeah, because everything in set A is contained in set A. We can say a set is a subset of itself. Trick one. That right there, 0 with a line through, we call it the empty set. It is the set that contains nothing. Now, we don't put 0 because 0 is an element, it is a number. So if we said 0 was a set containing 0, actually does have something. It has the number 0. So we draw the 0 with a line through it because, especially in sets, it's considered the empty set. It is the set that contains nothing. Is the empty set a subset of A? It actually is, because nothingness, yes? There's nothing in it. Well, yes, the empty set is a subset of everything. Because this classroom, we said, is a subset of the high school, yes? If no one was in this room, and there was nothing in it, would it still be a subset of the high school? Yeah. Just because there's nothing in it doesn't mean it's not a subset. We kind of get that, yes? So this is true. Okay? We ready to expand our brain just a little bit? How about the set containing the set containing the empty set? Is that a subset of A? Well, yeah, it's just a set containing a set that contains nothing. So that would be a subset, yes? Are y'all starting to see the dangerous path we're about to walk? Because if the set containing the MC set is a subset, and we can say that the set containing the empty set is a subset, then we could also say the set containing the set that contains the empty set is also a subset. Is there a limit to how far we can go with this? No. And we can do it indefinitely. Now, will we see this after this point? No. Because for when we start talking about subsets, we're going to talk about listing, especially the next part, listing all of the non-empty subsets. Because if we try to list all the empty subsets, there are infinite. We can just keep putting an empty set in that set. Okay? But really, it's physically you wouldn't be able to do it, but it's almost like if this room was completely empty and we built an empty room inside this room, it would be the empty set is still contained inside this room, yes? Then we can build an empty room inside that room, That's all that's doing. Okay? Last time we talked about it ever in here. Okay? So let's look at non-empty subsets with this example, because we're going to make some. All right? If I'm getting ahead of myself. If set A contains AB, and set B contains A, B, C, can we say that set A is a subset of B? Can we say that B is a subset of A? No, because set B has CD, yes? Doesn't work. Okay. This is what I was thinking of. Writing subset and set interval notation. So we want to write all the non-empty subsets, because we saw just a second ago how many empty subsets we can get. Way too many. So if we look at this first one here, we have the set containing 4, 5. Yes? What is one subset of this? The set containing 4, yes? Is that a subset of the subset, or of the set 4, 5? What's another one? 5. We can have the set containing 5. What else could we have? The set containing what? Well, not nothing, because right, because we do have that if we wouldn't, because the empty set we won't conclude, because we told it we don't want any of the empty sets. So far we have the set containing 4, the set containing 5. But we could also have the set containing what? 4, 5. Because as we said already, the set itself can be a subset. So here we can have a set containing 4, because that is a subset of 4, 5. We can have the set containing 5, because that is indeed a subset of 4, 5. Or we can have the set itself, 4, 5. Questions on this so far? So let's look at the next one, CD. What's one of the subsets? C. What's another one? D. Or we can have CD. We feel good with this here. So when we have 2 elements in a set, we get 3 subsets. It's not too bad. We ready for the next one? Now we're looking at the set that has 2, 4, 6. What's one of our subsets? 2. Then 4. And then 6. So that right there, the set 2, then the set 4, the set 6, that is all of our subsets that contain exactly 1 element, yes? We can also have subsets that contain 2. So what's the first one we could have? Say 2, 4. Let's keep 2 first, and then we could have what? 2, 2, 6. And then 4, 6. And for us here, and for how we're going to look at this, that is all of our subsets that contain 2 elements. Because for us here, we're going to consider that 2, 4 and 4, 2 are the same thing. Okay? Does that make sense? Because there are some situations where 2, 4 and 4, 2 are not the exact same thing. Okay? And part of the reason for that there is, you know what? I'm going to start on the center of this mat. As 2, 4, if we're talking especially in directions, if the first number is forward, and the second number we'll say is to the right. So if it's 2, 4, I'm going to take 1, 2 steps forward, and then 1, 2, 3, 4 steps to the right. I get to a certain location. Where 4, 2, if we put it the other way, still starting in this spot, it's 1, 2, 3, 4, and then 1, 2. Did I end up in the same location? No. So permutation, that operation is going to give us 2 different elements, or 2 different groups, if order mattered. Here it doesn't. But we will pick up this tomorrow.